All right, so here we go, our plan for today. We're going to do units, sig figs, like temperature and stuff like that, a lot of like random stuff. But ultimately, sig figs is the most important part of the day because you need to know those and use those and apply those rules to the rest of this class, and especially for the AP test. All right, so the objective, use proper units, report numbers using correct sig figs, and kind of, I probably should have also put to use scientific notation to report your numbers. And look, I went to high school and I had this lecture 20-something years ago, and I thought it was stupid. And then I went to college, I got this lecture in like every science class I went to, and it didn't get any better, and I've always just thought, these are ridiculous. And I still do, but they are required. So, you signed up for AP, so there are some requirements that we have to do. They're not that hard. That's the one thing I have learned in 20-something years. If I would have just had a better attitude, every time my teacher said sig figs, I probably would have known them and done them a lot easier. Because they really are not that hard. But they are very important. Let's see. Here's the reason they are important. It might be on a slide later. But we're going to assume all of you in here want to pass the AP test. Generally speaking, all of the free response questions on the AP test are out of 9 points. And I don't know why it's 9, but it is. You get one of the 9 points by using the correct units in your answer. You get a second point for using the correct significant figures in your answer. So 2/9 of your score on a problem have to do with the correct units and the correct sig figs. And the reason why that's super important is because if you can average between 4 and 5 out of 9, you can pass the AP test. Sound familiar? I just had this conversation. All right. Most of you are just coming to me. Is this like crazy or what? All right. I'm recording. I don't want to. What did I just kick? Here. Heather, pass those out for me. All right. So look, half of the score that you need to get to pass can just come from the units and using the proper sig figs. Here's some good news. You can have the complete wrong answer, but if you use the right units and number of sig figs, you can get 2 out of 9 points. So it's not that super bad, right? We got this. So, first thing first, we're just going to talk about units. So, this lecture is kind of weird because we're going to actually talk about units when we get to them. So each chapter, like, we'll talk about molarity and we'll talk about that unit. We'll talk about wavelength and we'll talk about that unit. So you don't have to write this list down and memorize them, but it's just kind of our base where we're going to start. So the SI stands for Système d'International, and it's French. But a long time ago, people decided it would be very valuable if everyone out there measured things the same way. So they came up with this standard way to measure things. And we're America, so we're too good to follow the rest of the world. So we don't use this, but we should. All right. The SI units, and we will use them in this class. We never use like Fahrenheit or feet or miles or anything like that. We use SI units. So for mass, the SI unit is the kilogram. Now, it really doesn't matter if you put kilo. It's anything that ends with grams. Anytime we use mass, we're doing grams. Not ounces or pounds or anything stupid like that. We're going to use grams. For length, we have the meter. And that could be a kilometer, it could be a centimeter, it could be whatever, but it's something ending with meter. Okay with that? In time, we always refer to time in seconds. That's pretty standard everywhere. Temperature is Kelvin. And we'll talk about Kelvin and temperature on a different slide. Kelvin is an absolute scale, which means it has a 0. The other scales have negative numbers. So they're not absolute. And then what do we have next? We have a mole. A mole is one of the weirdest units that we have in chemistry. And it just measures stuff, or numbers of things, or an amount of substance. This is the definition of a mole. 1 mole is equal to 6.02 times 10 to the 23rd whatevers. It could be atoms. That's typically what we're talking about, or molecules. But it could be desks. It could be pieces of sand. It could be computers. All right? A mole is just a word that means a number. In your life, you are familiar with the word dozen. It means what number? 12. And there can be a dozen of anything, correct? It's not just donuts. Dozen applies to everything. Well, a mole typically refers to atoms or molecules, but it could really mean anything you want. It's just a number that really means a big, big number. A 6 essentially and 23 zeros behind it is a mole. Okay, current is amps, and we'll do that way, way, way down the road in chapter 21. And then luminosity we don't really use. It's called a candela. And then volume we'll come up to, but that's just the liter. All right, these are just basic standard units in the SI system. All right, the power of the metric system is that it's based on tens. You just move the decimal one place to the other when you convert. And yeah, I go back for like 20. Good? Awesome. Okay. So what I was saying is that the metric system is based on tens. They're all 1 times 10 to the something. We are just moving the decimal place over. And these are some standards. Once again, don't memorize this. In chemistry, we really use 3 or 4. And it just depends on where we are at. And when we get to those, we'll get really good at those. But some standards are your giga and mega. And you're familiar with those just because your phone storage, your computer storage, or your internet speed. Then kilo, you've heard that probably a lot. Kilogram, if you watch movies, that's how they sell drugs. Deci, you probably haven't heard. Centi, you've probably heard of a centimeter. A millimeter or a milliliter, you've heard of those. A micro, maybe not. A nanometer. You usually only hear about that when they talk about the speed of light. Pico and femto, those are starting to get used a little bit more because of computer speeds. But we won't use those in this class. We will use this symbol called mu. It's this thing. Once in a while, it's mu is how you pronounce that, which is fine because it looks kind of like an M and kind of like a U or a mu. All right, next up is just volume. And don't write this down, but volume, we typically define it by a milliliter. And a milliliter is a box that's 1 centimeter by 1 centimeter by 1 centimeter. If we have 1,000 milliliters, we have a liter. All right, so now, and this slide show's all sort of mixed up, but that's okay. We're going to talk about uncertainty in measurement. Now, how many of you watched the video that I wanted you to watch overnight? 1, 2, 3. Awesome. 4, it looks like. It talked about significant figures, and if you want credit for that assignment, you have to watch it by midnight tonight. It's called Sig Figs or something like that on Edpuzzle. If you didn't know it existed, then turn on Canvas notifications on your phone, because then you'll get just a little pop-up, and it'll be kind of nice because you'll know what we're doing. All right. So this whole idea of significant figures has to do with uncertainty in measurements. All right. When we measure something, depending on the tool we use, the measurement might be super accurate or it might be hardly accurate at all. So if we look at, these are all measuring volume. A graduated cylinder, this one has graduations every 5. So it's sort of accurate, but not extremely accurate. This syringe, it has graduations probably every 10th. So it's significantly more accurate than that graduated cylinder. This burette, it has a mark every 10th, all right? Not 10th, every 1st, it looks like. I didn't even read that right. There might be marks in between, I can't tell. This pipette probably has a mark right there, and that's it. And this volumetric flask, these are mostly worthless. They are only good to measure one specific value. Like a volumetric flask is always labeled with a number. So it would be like a 100 milliliter volumetric flask, and that line right there would be where 100 milliliters is. And there's no other graduation on it to measure. All right. So since we have a lot of different ways to measure a measurement, when we write that measurement, we have to tell whoever's going to read it how accurate the tool we used was when we read it. I know that sounds a little bit confusing, but the way that we will do that is through significant figures. Significant figures, they deliver two things. They tell me like the value of the number, and they tell me how accurately I know that number. Whatever, I don't want to write that word. So if I had this, I would say I measured 100 milliliters. And people would know this is not an accurate value. It's around 100. If I use this, I'd have 46.5. And that none of those look good. 46.5. A person interpreting would know that you only know that it's 46 point something. This syringe, if I reported this value in sig figs, it would probably be like 5.325. And that would mean that I knew I used a very exact tool, and I know the two. When we do significant figures, we report the value with everything we know, and then one number that we estimate. And that is to help the interpreter know the value and the accuracy of the number. All right, we'll come back to that in a minute because these are just out of order, but no one really cares. All right, so the next thing we're going to talk about is just temperature. And just the standard definition of temperature is that it's the measure of the average kinetic energy of the particles in a sample. Pretty simple. All right. In scientific measurements, the Celsius and Kelvin scales are most often used. And all year long, we're going to have some weird symbols. Because some years, depending on the computer update, it will read that font that was made in, and some years it won't. And we're going to get some weird fonts. Like one of them, in like chapter 19, there's a mailbox in the equation. Like, what's a mailbox? But whatever. All these are saying, this right here is 100 degrees Celsius. That's all it's trying to... Right. These PowerPoints were created by the people that wrote the book. And they sent them with me. But my computer doesn't have those same fonts. And fixing them? No. I'm sorry. It takes forever. All right. Celsius is based on the properties of water, where 0 is where it freezes and 100 is where it boils. Kelvin, which is what we are going to use, and you should get good at this. Just a number you should memorize. You don't need to worry about the 0.15, but you should memorize this. The Kelvin scale is the SI unit of temperature. It's based on the properties of gases. It relates to Celsius. Kelvin is equal to Celsius degrees plus 273. All right? The two most common temperatures of Kelvin that we'll use in this class are 273, and that would be 0. That's when water freezes. Or we use 298, and this is the most common one. 298 Kelvin is what we consider to be room temperature. Right now, in this room, it's a little over room temperature, I'll assume. But typically speaking, room temperature is 72 degrees, and we're at 76.6. 72 Fahrenheit is roughly 25 degrees Celsius, and 25 degrees Celsius is 298 degrees Kelvin. Most math that we'll do will happen at room temperature, so you'll use 298 in your math equations for, it's mostly Chapter 10, but we'll use it a ton in Chapter 10. Anyway, if you can just remember, Celsius plus 273, your life will be fine. Good enough? Okay. We never use Fahrenheit, which you should be grateful for, because no one wants to find 9/5 of Celsius and add 32 degrees. That's just a waste of time. Or 5/9, F and minus 32. And it's a good time to make a plug for your calculator companies. Really, you should have calculators that are high quality enough that they'll do all the conversions for you. Here are 3 types in my life. I bought this one 20 years ago, and it will do all my math for me. Yeah, that'd be awesome. All of these have what we call conversion factors in there. You can convert from one unit to another, and you can convert on the metric scale. If you don't have a calculator that has these functions, you should invest in one. You will use it, if you go to college, you will use it for the next 8 or 9 years, depending on how fast you get through. If you're going to be an engineer, HP calculators are amazing. If you're going to do anything else, just get a TI. They don't even look like that anymore. Just get a TI. That will do everything you want. But if you're going to be an engineer, I would get an HP, because that's what all the people in engineering will do, and it has a lot more functions. But they're more expensive too. But then, if you have a converter, you don't have to memorize this stuff. You just push 3 buttons on your calculator. Okay. Just a review of density. You've probably learned density in your life before. Raise your hands if you've seen density. All right. Have we talked about it in this class? Probably. Not much, but I bring this slide up because we're going to use it later, but please. Okay, that was not what I meant to do. Oh, okay, we're just going to leave that there. I want to teach you something, and some of you may already know how to do this. It's not something that's required, but it will help you so much if you will just do this. In this class, we're going to use a few equations where there are 3 variables. If you take a physics class, you're going to use 100 where there are 3 variables. If you ever see a 3-variable equation, to save you from doing stupid things, I want you to put a circle and then divide it into 3 parts like that. If you're taking notes, put that circle just like that. I personally call this the Tom circle, because that's my name. Whatever. Now, the reason we do this circle is because even though you're smart, you suck at algebra. Even basic algebra sometimes. All right. What you do with this circle is you take the thing that's in the top and you put it on the top. And then the other 2 variables go on the bottom. And then you're ready to roll. Because who has screwed up on math before? Everyone has. If you're not raising your hand, you haven't done math. All right? You're going to be in a hurry and you make silly mistakes. So what the Tom circle will do is eliminate those mistakes, or at least lower the odds. What you do, because if you're asked for density, great, it's mass over volume. If you're asked for mass or volume, though, then you have to move the equation around, right? This circle will help. what you do is you cover up the thing that you're being asked to solve for. So we all know density is equal to mass divided by volume, right? So you cover up D, and it will tell you that it's m over V. If you're asked to solve for mass, you cover up the m, and you now know it's D times V. If you're asked to solve for V, which is what most people screw up, it is mass divided by density. Easy enough? When I ask for volume, 50% of you do it the wrong direction. Just write this circle covered up, it's m over D, not D over m or D times m. Sam, you got a question? Okay. Does this make sense? In physics, you'll use 100 of these. And I know you're not in physics, most of you yet. But a simple one in physics is force equals mass times acceleration. There are 3 variables. Draw the circle. Put the little t in it. And then this time, if you notice, there is nothing on top, correct? But that's okay, because you know m is times a every time. So m and a go on the bottom, and that must mean what's on top? Your force. And now you would be ready to roll. So acceleration would be force divided by mass. Mass would be force divided by acceleration, and force would be mass times acceleration. This might not seem useful right now, and you're like, why is he teaching me algebra? Well, it's because I suck at algebra. I know how often I knew how to do something in my head and then did it wrong on paper, because algebra is just rude. It'll slap you in the face as soon as you think you know what you're doing. Okay, are we all right with that? Later today, if we have enough time, we'll get to a density equation where we ask for something besides just density, and we'll work through that. Okay, the rest is now significant figures. Significant figures, like I said at the very start, they are extremely important if you plan to pass the AP test. They're extremely important if you plan to get an A on my test. You could probably get an A minus or a B without using any sig fig rules on my test. But most of you are AP kids and you don't like A minuses. So, the term significant figures refers to digits that are measured. And when we do chemistry, almost every math thing we do has measurements in it. We're not just a math teacher that just makes up math problems for fun. We're solving real life problems. Okay? Now, I know they're written in the textbook, so they're still fake. But whatever. You are in physics. Look at that. I just saved your bacon. They'll probably teach it too. All right. So, when rounding calculated numbers, we pay attention to sig figs so we do not overstate the accuracy of our answers. All right. In significant figure rules, it's all we know and a guess. What's that? And a guess. I'll talk about what that means. What? Yeah, the last figure is always an estimated guess. So they where? Oh. Just put them upside down in that strainer, and I'll let them dry and then put them away later. All right. So an easy way to illustrate how we do a measurement in significant figures is just to talk about height. So, I don't know. Who's the taller? Which one of you two is taller? Just stand up. All right. Well, all of you estimate his height. We'll just write it down on your piece of paper. Write it on your paper. I don't think he's 6'1", personally. 6'7". I don't think he's 6'7" either. Okay. You can sit down now. What? You can't stand up. All right, now, Caitlin, will you stand up? Oh, yay. Will you estimate her height? Short? That's not a number. All right. So, you can sit down now. All right. How many of you guessed 6 something for Dane? 5 something? 3 of you? Holy cow. How tall are you? 6'4". If you guess 5 something, you got to work on your estimation skills. How tall are you? But you guessed he was 5 something? Okay. I definitely went with the wrong person taller, but it's fine. Almost everyone guessed 6 feet. And then raise your hand if you guessed 6'0". 6'1", 6'2", 6'3", 6'4", 6'5", 6'6". Okay. What this has to do with significant figures is it was pretty easy. Now, not everyone guessed 6, but it was pretty easy to guess the first one correctly, right? We know he's 6 feet, but then we don't know exactly. So what was the 0, 1, 2, 3, or 4? That was our guess. Did anyone write down like 6'2" and a third? No. If we throw on that extra little part at the end, that would mean, like if I read that someone was 6'2 and a half, I would really think, wow, they know exactly how tall they are, right? But most of us just guessing a height. We would never include the half because we don't know. We're guessing. Caitlin, how tall? 5'0". How many of you guessed 5 something? 4? Anyone? 4'11". All right, we're all right. 5'0". Hers should have been harder because that is right on the cutoff. But still, generally in our minds, if people are tall, they're 6 feet something, right? If they're short, they're a really low 5. Very few people in high school are 4 anything, correct? So we can pretty much accurately know that first number, and then we guess. When we do measurements, depending on the tool, we will know certain things, and then we always throw on a guess. Significant figures, once again, they're just written so that I know the value and the accuracy of a number. I know it's not fun, but it's not that bad, ultimately. All right. Nope, I am done. You are done, I mean. You are fantastic. All right. Now, you ready to go? We're going to use it in a ton of math situations. Now, we got to be careful. Math class never uses this. But math, and I'm not trying to be mean, math just itself is useless. Because no one just is like, oh, I wonder what the square root of 8 times 5x is. Like, that's useless. But when we start to solve word problems, which no one likes because they're harder, but we actually start to apply math to solve a problem, then there's value to it, and it'll make sense. Now, to make one up in my head, no, but there's one coming up. All right, so here we go. I am using this presentation to teach and encourage you to learn how to use 2-column notes. And I know that's kind of weird. You're like, isn't he a science teacher, not an English teacher? But in AP Chem, there's a lot of times where I'm going to give you some rules or some steps, and then we're going to do example problems. Have any of you ever done an example math problem in class and then gone home and tried to figure out what you did again? And you have no idea? Like, that's the story of my life. So then I'd be like, in class, I'm like, why am I even writing this down? Because I'm not going to know what it means in 2 hours. 2-column notes tries to help you with that. And I'm not saying you have to do this, but I'm encouraging you that especially in mathy chapters, which is most of them, that you use the idea of 2-column notes. The idea of 2-column notes is that you divide your page in half. And I wouldn't really make it a half. I'd have it like 3/4 and 1/4 or whatever. And on one side, you put the notes, all right? And the notes here are the rules that we're going to follow. And then the other side are the problems where we're going to apply those rules we wrote down. There's a lot of power in 2-column notes when you're working through a lot of examples. Because then your example is right next to your notes versus vertically and even sometimes on the next page. If you put it next to your notes, life will be a lot better. Okay. You don't have to do it, but I encourage you. All right, so here we go. Significant figures, and if you watch the video, all these rules were there, and I hope it was helpful. So here we go. The first rule is that all non-zeros are significant. Now, we need to be able to do two things with sig figs. We need to be able to look at a number and determine how many significant figures are in that number. Just that thing is a skill we must have. And the second skill we have to take a number and look at it and be able to write it in scientific notation with the correct number of significant figures. Both those skills are necessary, and if you'll stick with me, I feel like I'm pretty good at teaching this, and that you'll all be fine if you pay attention. And this is why that's on the wall. Stick with me. My TA last year had me for chemistry, AP chemistry, and then she was my TA. And she says I said the word stick with me 5,000 times, which is probably true. But I know what I'm doing. I know that sometimes we have a straight up lecture and it's boring. But if you can stick with me and get through it, it will help a ton. All right, so here we go. Rule number 1. All non-zero digits are significant. So if the number is not a 0, then it counts. So in the 581, how many sig figs are there? There are 3 significant figures. So that's the first skill we have to have, is just determining the number of significant figures. The second skill, remember, was to write it in scientific notation. In scientific notation, this number would be 5.81. I have to account for the 3 significant figures times 10, and then you just move over. 1, 2, 10 to the second. That would be this number written in correct scientific notation. Those are the 2 skills. You have to identify that there are 3 sig figs, and you have to be able to write it in scientific notation. Now, I don't require that every answer be written this way. Like the number 10. 10 is 1 times 10 raised to the first. Well, that's dumb. Just write 10. Okay, I don't require that you go overboard, but there are some numbers that are giant, like that number I showed you for a mole. No one wants to write 603 and then 21 zeros after it. So this one you do want to write in scientific notation, just to save you time. So the general rule for me is write it in whichever one's easy. 10 is 10. Avogadro's number, 6.02 times 10 to the 23rd. Or that's what mole was. Okay, here we go. Are we okay with the first one? That's the easiest one. If it's not a 0, count it. All right. These sometimes are called sandwich zeros. Oh, Tom, come on. Zeros between 2 significant numbers are themselves significant. So both of these zeros in here matter because they're between non-zeros. So this number right here has how many significant figures? 4. Every single one of them is significant here. And to write that number in scientific notation would be 1.005. I have to account for every significant figure times 10 to the 1, 2. Okay? So far, okay? All right. Next. So those are easy. This one typically isn't hard. This is the only one that really causes fights. This one. Zeros at the beginning of a number are never significant. All right? So I'm going to cross out every one of these zeros, and once I get to a non-zero, then it's everything else after. So this number has a total of how many significant figures? 3. And that matters because I would write this number in scientific notation with 3 significant figures, 5.78 times 10 to the 1, 2, 3, 4, 5, 6. And that'd be negative because we went from left to right. That's freaking me out. We're not done. Ooh. Okay, scared me. It's like I'm not even there yet. All right, are we okay with that number? Zeros at the front never matter. Those zeros, if you think about what they're doing, they're just holding place values. They have to be there so that these 3 numbers are in the right place. Now, where people get fed up is right here. Like, this is stupid. And I know, like, in your calculator, if you type 1200 or 1200 point, does that matter to your math at all? No, I realize that. But they do matter because this number is way less precise or accurate than this number because of the decimal. So here we go. Zeros at the end of a number are significant, and there's a big word here, by the way, if and only if a decimal point is written in the number. So, since there is no decimal point here, these 2 numbers don't matter. So there are 2 sig figs there. This one, since there is a decimal point here, those numbers do, or those zeros do matter, so they're 4. This decimal implies that we know this number to that place. The lack of a decimal here means we know it's somewhere between 1 and 2,000. That's a pretty broad range. It's somewhere between 1 and 2,000. This one means it's somewhere between 1,200 and 1,300, which is a lot more accurate. Okay. What do you think? Manageable? I know it's weird, but we can do it. Now, there is another rule. It's not sciencey at all, so some of you might like it. You'll just look. If you see a decimal in a problem, you start from the left, moving to the right until you hit a number. And everything else after that is considered significant. All right? If, I'm going to rewrite 1,200 down here. If the number does not have a decimal, you draw an arrow from the right to the left until you hit a non-zero, and you count those. All of those numbers is significant. Okay? And that's not like the technical way, but if that works for you, do it. I don't care how you do this, just do it. Because the decimal implies what we know. In this problem, and this might not clarify it, but this is the answer. In this problem, this 0 is my guess, which means I know those 3 numbers, right? In this number, the 2 is my guess, which means I only know that number. So the range, like on a test, the range of correct answers for this would be between 1,000 and 2,000. It's a pretty broad range, right? But this one would shrink it way tightly down. It's just to put your estimate. So like for her, all of you guessed lower, right? So all I know is if all someone wrote was that Caitlin was 5'2", I would just know, hey, she's a low 5. The 2 would tell me she's at the bottom of that scale. but she could be a 0, a 1, a 2, or a 3, or a 4. If someone said she's 5'9", then the interpreter would just know, well, she's a tall 5, but we only know the 5. What we did yesterday, like our stuff. Okay. Yeah, I can. We used this super precise scale, right? The reason why we did that was so that our percent errors were a lot lower. This measures to the 10,000th place. And before I used this, we would get errors of up to 200 or 300%. Because when we're measuring the iron, do you have your result for iron just randomly? Okay, but what was its mass? It was small. We know that, right? So, anyone have their mass of iron? Okay, that sounds great. 0.0532. Okay, well, I'll take it. That's good enough. Okay. Well, this means that I know it to here. The other scale would only measure to there. So its accuracy was 10 to the second, or 100 times less accurate. And when you're measuring something that only is in the 10th place, we might as well be at 0. Like the difference is, not the difference, the amount of error that could exist with a less accurate scale is off the chart. So buying a $3,000 scale that goes to the 10,000th place got most of our percent errors to under 50%. In this problem, no. The last number written is always the estimate. Then any number would be correct on a test or a measurement. Yeah, then you're like, hey, I'm in the same ballpark they were. And think about it. If we're doing a measurement and we're only off like 3 10,000ths, who cares? That's like my hair. But if I'm off 3/10 and the thing was 5/10 itself, then I'm 60% off, and it's a huge difference. Yeah, exactly. Because all this eventually has to do with how are we going to round this crap? And all of us have to follow the same rules, or we'll get like 20 different versions of the same thing because you rounded incorrectly. But significant figures will give me the exact number that we all will have, and then we round the same. That was really good questions. All right. So in your 2-column notes now, if you're doing them or wherever you are, here are 5 problems. All we're doing on these 5 problems is determining the number of significant figures. You don't have to do anything else. So it's just going to be like a value, just one number. When you are done, will you check with your lab partner and see? Check to see if you agree. When you're done and you've talked, will you just raise your hand and put it down so I know who's done? Last hour I moved on, like right now. Like 2 people were done. Michelle, you good? Liam, good?
Oh boy. You can absorb it.
All right, so this number has a decimal, which means I come from this way, and how many are left now? 3 sig figs. If there is a decimal, zeros at the end count. How many of you had 3? What? It's 3. If there's a decimal, zeros on the right count. They don't hold value, but they report accuracy. What we... Yeah, they're way different. You should watch the video on Ed Puzzle tonight. What one don't you like? B? Is there a decimal? Yes. So numbers at the right matter if there's a decimal. What, Leah? No decimal, just 1. It is. Look, these will come. And you can think they're dumb your whole life, which I mostly have, but they're doable, and we'll go over them. There's that video tonight. Please watch it on Ed Puzzle if you haven't. There's also on Canvas, right here. I think it's the next slide. On Canvas, there's a link to this practice site where you can do 1,000,000 of them if you want. All you hit is your new problem. And then you put, whoops, the problem is right here, 9.570 times 10 to the 4th. So you put your answer in right there. This one has 4 sig figs. Check answer. You'll see whether you're right or wrong. There's a lot of practice, but please watch that video on Ed Puzzle. It's worth points, and it's due by midnight. You can find that link on Canvas. It's just on the page that's on sig figs, if I remember right.